Let's continue with the vestibular pathways. First of all, some revision is needed, and that includes the labyrinth, both bony and membranous labyrinth. You can recall the different parts of semicircle of the labyrinth, like semicircular canals, anterior, posterior, and lateral semicircular, containing the semicircular ducts, of course. The ducts are connected with the utricle. This is connected with the saccule. These are occupying the vestibule of the bony, inner ear bony labyrinth, and connected with the saccule is the cochlear duct, which turns up in the cochlea. These are the things to be recognized at first. And one thing is a clue for understanding or for orienting yourself in the histological slide of the inner ear, if it happens to be your slide on the final exam, and that is the axis of the modulus, the axis of the cochlea. You remember that cochlea has got a wider lower basal turn, and the radius of the turns get reduced till the apex of the cochlea, apex of the modulus. Therefore, you can determine this axis of the modulus coming from the base towards the apex, and this axis is directed anteriorly, laterally, as well as down, but in the slide you won't have the third dimension. The receptors for the vestibular perception are of two types. One is responsible for perception of angular acceleration of the body or the head separately, and these are the ampullary crests, pistae ampullaris, and these are located in the ampullary widened end of each of semicircular ducts. There is one anterior, one lateral, and one posterior, as the ducts are the same. Please note that those of the anterior and lateral are fairly close to each other, while that of the posterior semicircular canal is farther separated from them. You understand that these dimensions are equal to millimeters or parts of the millimeters only, but this has got a little bit of importance for the future learning. The movement of the body in a linear direction is perceived by specific receptor organs, both in the utricle and the saccule, and these are the maculae. So there is one macula of the utricle, macula of the saccule, and these are responsible for perception of linear acceleration of the body. The position of semicircular canals are to be revised again. Knowing one thing helps you a lot, and this one thing is the orientation of the axis of the pyramid. As you know from the first semester, the two axes of pyramids converge anteriorly. It means that the pyramid is pointing anteriorly and medially. Related to this axis, you can give the position of the semicircular canals. Two of them are vertically oriented. One is the anterior, being perpendicular to the axis of the pyramid. The other is the posterior, being parallel with the axis of the pyramid. And the third one, the lateral, fits into more or less the horizontal plane. One thing is to be emphasized, that in normal anatomical position, the plane of the lateral semicircular canal is not exactly horizontal, but tilted something like 30 degrees upward anteriorly. This has a practical reason. When the information produced in the lateral semicircular canal is needed, this one is mostly during walking, and when you start walking, you bend your head by roughly 30 degrees down to look not immediately in front of your feet, but 2-3 meters away from your feet. You should look at, and you should be aware of the visual as well as the visual information coming from that part where you should walk to. Another important characteristic, that the anterior semicircular canal of one side is parallel with the posterior of the other side, and both of the laterals are horizontal. These receptor organs, the maculae, have got very unique built-up morphological characteristics. So this group of receptor cells either bend in shape, and P part of the organ being horizontal, the other part fitting into vertical plane, and that is the feature characteristic for macula of the utricle, while macula of the saccule is a small hook-like area completely fitting into vertical plane. Both of these organs have got a central region which is either a depression, a groove in the middle, or an elevation in the middle, groove in case of macula of the utricle, elevation, ridge in case of macula of the saccule. The important thing is that the orientation of the hairs is very strictly determined, related to these central portions, which in both cases are called the striolae. So striola in one and striola in the other receptor organ. Going into details of morphology of the hair cells, the receptor cells itself, in general you can distinguish two of them. The differences are readily visible in the nice illustration of Professor Kestic. These are held in position by supporting cells everywhere, and the supporting cells together with these apical portions of the receptors make a complete ceiling at the top of the organ itself, which of course has got the hairs hanging into the space full of endolymph produced in the cochlear duct. So the two types are similar in one aspect, and there are some differences between them. Similarities are that at the apical portion, both of them have got processes hanging out from the surface, from the apical surface. One of these processes is a beautiful, typical kinocilium. The proof for that is the basal body, the centriole, in which the microtubules are anchored, and all the rest are stereocilia with decreasing length away from the stereocilium. Slight difference is that the processes of the flask-like cell are twice as long as those of the bottle-type cell. Another difference of them is that being secondary sensory epithelial cells, these hair cells have no process to reach the central nervous system. Therefore, afferents should reach here and take the information from them. The afferent around the flask-like cell is something like a mug, completely having the cell body of the receptor inside, so surrounding it. And the other case, these the afferents are just small contacts with the receptor cell itself, with the hair cell itself. In both cases, the sites of synaptic transmission are unique, something like we saw in the visual system. Then there are synaptic bars surrounded by the small synaptic vesicles in both cases. And one more important thing is to mention, I know it's early, but the illustration shows very nicely that as for all the sensory systems, the central nervous system talks back to the sensory cells, either to the sensory cells directly or to the afferents taking the information from the sensory cell. So these are efferents coming from the brainstem. The orientation of the processes I told you are strictly determined, and these are related to the central part of the receptor organ, to the striola. In case of the macula of the utricle, the kinocilia are always on the side of the cell which is closer to the striola on both sides. The opposite applies to the macula of the saccule. When away from the striola, the kinocilia are studied. On top of the hair cells, there's a beautiful membrane which corresponds in structure to that of the tectorial membrane in the inner ear, but this is fully packed with extremely small crystals, and these crystals are calcium carbonate crystals, mostly hexagonal in shape, and because of these crystals, because of these stones, if you want, the lithos is stone. These are together with the amorphous material. This is called the otolith membrane, into which the hairs are involved or pushed in. Here you can see electron microscopical picture of these beautiful calcium carbonate crystals. Professor Kirstich has lifted the membrane away, so in normal situation the membrane is immediately on top of this layer produced by the supporting cells and the receptor cells itself. Here you can see the mug-like shape of this afferent belonging to the flask-like cells. Ampullary crests are a bit different. In the ampules of the semicircular canal, these are, and one from the posterior semicircular canal is depicted in the lower picture. This one is the wall of the semicircular duct itself, and that is the bony wall of the semicircular canal. Don't forget that inside the duct is endolymph and outside the duct is perilymph, so the two different fluids are completely different. So these organs, the cristae, as the name suggests, these are elevations moving or located in a halfway turn on one side of the duct and protruding towards the opposite side. And these elevations contain the receptor cells. These are again hair cells, and the receptor cells have got almost the same features as those for the maculae. So two of them, two types exist. The gynoecilia and the stereocilia are much longer than those located in the maculae. Supporting cells surround afferents arise, so everything is completely the same. But don't forget that on both sides of this elevation, the receptors are found. Not like the otolith membrane, but like the tectorial membrane, something covers the hairs of the hair cells, and this is to be recognized in the histological slide as having no crystals on top of it, no otolith crystals. That's a jelly-like structure. And one thing is good to keep in mind, that opposite to the elevation of the crystal or crest, this cupula, that is the name of this amorphous material, this cupula is fixed to the opposite side of the duct itself. So not like before we thought that due to movement of the endolymph within the semicircular duct, the cupula is bent to one side and other side freely, like a door, for example, but it is kept in position in the opposite side of the duct. The gynoecilium again is located always at a certain side, one side of all the organ itself, the cristancularis. In the anterior and posterior, I told you that this one is taken from the posterior. In the anterior posterior, towards the duct, these are studied, and in the case of the lateral semicircular canal, towards the utricle, so towards this portion, the gynoecilia would be located. One thing is to be revealed. Since each of these semicircular canals, together with the utricle, they become complete circles. Therefore, in case of turning of the head in a certain angle, certain direction, the turning produces relative flow of the endolymph within the semicircular duct through the utricle, and this flow could either be directed towards the ampulary end. This is called the ampulopetal flow, and opposite to it, away from the ampulla, there is ampulofugal flow. And because of the specific orientation of the kynocelia, the ampulopetal flow is the one which makes activation in the lateral semicircular canal, and ampulofugal is the one which is a proper thing to be perceived by the receptor cells of anterior and posterior semicircular canals. This one is called the Ewell's law in general. One thing from the high school is to be revived now. The activity of a movement to a certain relative flow. So because the endolymph, by turning the head, wants to stay stationary within, and therefore relatively it changes its position within the semicircular canal. So one thing is to revise this cosinus equation. I hope you remember that cosinus 0 equals to 1, and the cosinus 90 is practically nothing, is 0. So in our terms, it means that if the movement happens within the plane of a certain semicircular canal, that produces the higher intensity of the blood, of the endolymph flow within. And if the plane causes 90 degrees with the plane of the semicircular, plane of the movement with the plane of the semicircular canal, that has no action, no activity is produced in that certain semicircular canal. Let me tell you an example. If you hold a bottle of beer within your hand, and if you make horizontal movement of this flask of the beer, then the foam on top of it practically wants to keep its position due to inertia. Therefore, turning to the right makes a relative movement of the beer to the opposite direction. So this is the case when the plane of the movement fits within the plane, fits with the plane of the perception, and that is the highest influence it has got to it. But if vertically, if you are moving the flask of the beer up and down, nothing happens to the foam. You should think of it thoroughly. The vestibular transduction, so how bending of the processes results in action potential of the hair cell. Before we mentioned that the utricle is responsible for perceiving the movement in horizontal direction, since the macula of the utricle, both being vertical and horizontal, in case of the horizontal movement, one part gets activated, and because of vertical orientation of the macula of the saccule is therefore for vertical movement this receptor responds. So taking one of these hair cells as an example, red indicates here the only gynocilium, and the greens are the stereocilia, being on the opposite side, of course. And on the top of each of these hair cells there is a thickened area called the cuticular plate, and due to bending of these processes, there is a small invagination of the membrane which produces a notch that is called the cuticular notch. The otoliths are needed to be embedded or being on top of the otolith membrane because they increase inertia of all the organ related to the normal density of the endolymph. Having the otolith inside, it increases by 3 times the inertia. Therefore, more sensitive, of course, the receptor becomes applying that load on top of the membrane. So there are 2 different ways of movements, bendings of the cilia. One is towards the gynocilium. If everything moves, then the result is the membrane deformation at the cuticular notch. The notch is produced, and this one is this is good for initiation of opening of ionic channels. So calcium moves into the cell, and that results in depolarization of the membrane. Due to depolarization, the glutamate is released towards the afferents, the sensory afferents at the bottom. While in the opposite direction movement happens, then the opposite side, this notch is formed towards the stereocilia, not away from the stereocilia, and that closes the ion channels, and hyperpolarization results in inhibition of the cells. So in the maculae and in the cristae, these act on the same way, on the very same way. Again, the action potential produced by the hair cells, how it reaches finally the vestibular cortex, if you want. So what are the parts of the involved pathway, the vestibular system? Anterior, posterior, lateral, semicircular ducts you can see, and canals you can see, which produce the action potential and give the action potential to second order neuron. In case of vestibular system, these are the first order neurons, and these first order neurons are situated within a ganglion, and this ganglion sits within the internal acoustic meatus, so not in the inner ear but in the posterior part of process of posterior cranial fossa. The ganglion is this ganglion of Scarpa, again consisted of bipolar neurons having central and peripheral processes. Through different nerves, the peripheral processes reach to the organs. Uticuloampullary is one of the divisions of the vestibular part of vestibulocochlear nerve, and this uticulo, as the name suggests, supplies two ampullary crests plus one macula, and this is macula of the uticle. Therefore, necessarily divides into three branches, and the three branches give the anterior and the lateral ampullary nerve and the uticular nerve. Another branch or two branches give afferents to the macula of the saccule. This one is called saccular nerve. And the third division of the vestibular part is the posterior ampullary, being destined to an ampullary crest away from the other two, therefore separately it should travel. Because the vestibular ganglion is within the fundus of internal acoustic meatus, therefore these three different divisions use openings on the fundus of internal acoustic meatus to get into the inner ear. Again showing the left fundus to you with the transverse crest previously mentioned and the ill-defined vertical crest dividing the four quadrants from each other. And now, because the anterior inferior was used for the cochlear part of the vestibulocochlear, the superior posterior and inferior posterior remained, at which three openings are for the transmission of the three divisions of vestibular. At the posterior superior quadrant, the opening is called the superior vestibular area, through which the uticuloampullary goes. At the inferior lower quadrant, there are two holes, one immediately below the transverse crest, crista transversalis, and this one is called the inferior vestibular area, while a bit farther separated from this, further to the back, but in the same quadrant, is a singular foramen, foramen singulare, through which the posterior ampullary can get into the inner ear. We did not mention before, just because you won't sleep well without knowing it, this anterior superior quadrant, what is it for? Here you can see an opening, and this is the internal opening of the facial canal. So now you understand why within the internal acoustic meatus in the first semester you run facial plus vestibulocochlear together, plus the labyrinthine artery. The vestibular part of the vestibulocochlear nerve reaches the brainstem at a place what you much known now. This one is the lateral recess of the fourth ventricle, and the floor of the lateral recess was called vestibular area. So no wonder that vestibular nuclei should be found deep to the ependyle. These vestibular nuclei are 4 in number, and I only indicated 3 because these are the termination sites of the primary vestibular afferents. The fourth nucleus is not amongst them. There is one superior, one inferior, and one medial vestibular nucleus. There is a topographic representation of different receptors or different receptor organs within these nuclei. As you can see in a schematic drawing, superior, medial, inferior vestibular nuclei, these are the only ones in which afferents from the inner ear terminate. And if you consider the termination of the ampullary crest, or cristae ampullaris, then in all the 3 nuclei you can find these synaptic couplings, while utricular fibers from the macula of the utricle only in middle and posterior, and those from the saccule only in the posterior, inferior vestibular nuclei, they terminate. So this is called vestibulotopy, related or contrary to the somatotopy or the retinotopy or the tonotopy previously you became familiar with. So just to mention the 4th vestibular nucleus, this is the lateral vestibular, but does not receive, don't forget, does not receive primary vestibular afferents. Second order neurons, or axons of second order neurons sitting in these vestibular nuclei, they give rise to axons which either ascend within one of the medial longitudinal fascicles, so either ipsilaterally or contralaterally they use the medial longitudinal fascicle. The other way is that through the medial longitudinal fascicle, of course, the fibers can reach the eye-moving nuclei, oculomotor, trochlear, and the abducens, which is hidden here, plus the interstitial nucleus of Cajal. The other way of these second-order neuron fibers is to go down. Going down, there is one medial vestibulospinal tract, which is a bilateral projection of second-order neurons, strictly from the same side, from the lateral vestibular nucleus. The lateral vestibulospinal tract originates, but this one, as we said before, does not contain second-order neurons, but further processed vestibular information is the one which reaches down to the spinal cord motor neurons, and this vestibular information mostly comes from the cerebellum. So cerebellum gets informed of vestibular information, and matching with other information together sends an order down to the lateral vestibular nucleus, which influences the movements of the muscles down there. Synaptic connections are to be discussed. So these are the specific nuclei involved, and the same nuclei are illustrated here, the 4 vestibular nuclei, eye-moving nuclei, and the interstitial nucleus of Cajal. And the first order neuron, 2 origins, either macular or ampullary origin they may have. They use different vestibular nuclei, as discussed before, according to vestibulotopy. The second order neurons sitting in these primary vestibular nuclei, axon of them, either through medial longitudinal fascicle go up, or also second order neurons can escape this system and directly terminate in the thalamus. In the thalamus, in general, 2 nuclei, mostly the VPI, the ventral posterior inferior, and at some extent the VIM, the ventralis intermedio medialis, also receives the secondary vestibular fibers. And from here, the third order neuron should originate, but the second order neurons, the blue ones, are the ones which the axons of them go down in the previously mentioned tracts to influence neck movements, neck position, and the posture of the body related to the actual vestibular information. From the VPI-VIM, the third order neuron is the one which reaches the primary vestibular cortex, which is restricted to the lips of intraparietal sulcus, so like the visual cortex surrounded by the sulcus calcarinus, calcarine sulcus. Here the intraparietal sulcus is surrounded both above and down by parts of the vestibular cortex. Involvement of the cerebellum in vestibular function is to be mentioned, so how cerebellum is informed about vestibular information. Here you can see that the fibers, the primary vestibular fibers coming from the vestibular ganglion of Scarpa, they may reach partly the fastigial nucleus of cerebellum, and most of them go into the flocculus. You remember that flocculus, together with the peduncle plus the nodulus, together where they were called the archicerebellum or vestibulocerebellum, and here you can see why. And another way to reach the cerebellum is through a synaptic coupling, so not first order but second order neuron is the one which reaches from the inferior vestibular and medial vestibular nuclei, from the inferior and medial, reaches up to the flocculus also, and to the uvula of the vestibulocerebellum. Simplified connections, synaptic connections are to be discussed. One thing what you can really expect, and we already mentioned tangentially, by the way of the descending connections of vestibular nuclei, medial from the three vestibular nuclei, lateral from the lateral only, they send down information to gamma motor neurons of the spinal cord, which are setting the stretching of the intrafusal muscle fibers, and therefore determining the contraction of the muscles responsible for posture of the body. Another important synaptic connection is involved in the vestibulo-ocular reflex. So one of the reflexes initiated by the vestibular system, and this one is eye movement as an answer for turning the head of the body. So therefore vestibulo-ocular is the name of it. In case of rotation of the head to the left, it produces activity, ampulopetal movement in the lateral semicircular canal of the left side, of course. In the right side, because the turning of the head fits into horizontal plane, therefore the lateral semicircular duct, the ampullary crest, is responsible for the perception. So this increases the excitement of hair cells of the left side, but contrary to that, on the right side, the result is inhibition. So turning the head to the left results in opposite movement in horizontal plane of both eyes. And for that one, you must see the synaptic connections of medial vestibular nucleus, for example, which sends axons to the opposite side. In this case, this is left to the right, abducens nucleus. From the abducens nucleus, the right lateral rectus muscle gets innervated, and therefore the result of contraction of it is turning the right eye to the right. But at the same time, synapses to interneurons within the abducens nucleus, axons of which recross the midline, so go back to the left side, and innervate that part of oculomotor nucleus of the left side, which is responsible for innervation of the medial rectus on the left side. So the result of contraction is turning the left eye to the right again. So left movement of the head results in opposite movement of the eye, and that is called the vestibulo-ocular reflex. You can investigate on anyone looking into your eye and asking the individual to turn head in one or other direction, and in the opposite direction the eyes are shifted. For the best result, of course, simultaneously, the antagonist muscles should be inhibited, and this inhibition is made by interneuron going almost the same way, ipsilateral abducent nucleus to inhibit the lateral rectus on the same side, and contralateral oculomotor inhibiting the action in the medial rectus of the opposite side. Bit complicated connections. I don't want anyone to memorize them, and don't advise to memorize them, just to show the complexity of the wiring of the brain and the function of the brain. So practically every point is connected to every other points in the brain. So making this a little bit more simplified. From vestibular receptors, the vestibular nuclei receive information. Here the information processing starts, and integration happens between the different informations coming from the vestibular nuclei and control of them. Vestibular information is sent up to the cerebellum, where this influences muscle tone and planning of movements within the cerebellum. The extraocular eye muscles also get order from, or get information from cerebellum, and through medial longitudinal fascicle from the vestibular nuclei, and in turn cerebellum, receiving the vestibular information, processes it and sends back to vestibular nuclei, mostly to the lateral vestibular nucleus, from where information goes down to spinal cord. So looking at the way of information from vestibular nuclei, not going up, going down to the spinal cord, extensor and flexor muscles are influenced. There is a direct connection of vestibular nucleus with the dorsal vagal nucleus, this parasympathetic nucleus of the vagus, and that is responsible for the innervation of GI tract. So this, for example, is the anatomical base, while vestibular information can result in nausea and vomitus of an individual. The muscles, information from muscles of the body through the spinocerebellar tracts reach back to the cerebellum, when again the summarization of information happens, and according to the new result, the new effect is executed. Also from the muscles, the reticular formation gets information. Reticular formation wants to know everything in the brain, so also connected, has got input from the cerebellum, as well as reciprocal connection with the eye movement, eye-moving nuclei it has got, as well as direct and reciprocal connection with vestibular nuclei. So any circle you choose, then you can see the complexity. Reticular formation now, receiving the vestibular information, sends down fibers to the lateral horn of the spinal cord, from where preganglionic sympathetic fibers reach the sympathetic ganglia, doesn't matter which one, and through these the postganglionic fibers innervating vessels and glands are responsible for pallor, for example, the whitening of the skin of the face, or the cold sweating due to vestibular information for a long time. Another connection what reticular formation has got it with the nucleus ambiguus, the ambiguous nucleus, fibers from where innervate pharynx, and this is responsible for regurgitation when everything comes up in the GI tract, regurgitation evoked by vestibular stimulus, and also has connection with the nucleus movement of the phrenic nerve, and the action of this excitement of these pericardia in the nucleus. One of the action is vomitus, because they contract, the fibers make the contraction or initiate the contraction of the diaphragm. It has got the reticular formation is connected with salivatory nuclei, so has got influence on the salivation itself. Of course, this one is the parasympathetic way of stimulation. And not to forget about higher connections as well. Cerebral cortex has got great impact in the function of the cerebellum. You remember the indirect pathway involved in the extrapyramidal system, which uses the pontine nuclei, so the corticopontine plus pontocerebellar tracts. By this way, the cerebellum gets information from higher centers, as well as the cerebral cortex, of course, has got influence on eye movements. And the cerebral cortex is informed of any other sensory information simultaneously, so taking them into consideration can send down information to both cerebellum and the eye-moving motor nuclei. So just to show the complexity of possible connections, that was it. Example for vestibulo-ocular reflex. One almost completely we discussed, but once more, turning the head to the left. This is the one which excites the left ampullary crest because of the ampulopetal way of the endolymph flow, and simultaneously in the right lateral semicircular canal results in inhibition. Due to this one, the final result is the opposite movement of the eye because of innervation of lateral rectus on contralateral side and the medial on the ipsilateral side. Now that one is involved in the optokinetic reflex, that is called the optokinetic reflex. Everyone can exercise this, because if you look at the eyes of someone looking out from a window of a train or something like that, the gaze wants to fix something in the visual field for a while. Therefore, as the train passes by, in the opposite way the gaze is oriented, and after a while there is a sudden movement back of both eyes simultaneously, and this is the nystagmus itself, these saccadic eye movements. One slow phase is the one which follows, and one fast phase which results in returning of the eyesight. That is the reflex itself. The other important reflex in which the pathways are involved is the dorsal maneuver. I don't know whether you know this, but this small baby doors, what lady girls want to have, these have got eyes which are closed when the baby is bent to the back and open when it is stood up, and this one is could be investigated in humans as well. So turning the head to one side results in movement of the eyes in the opposite side. And the other important investigation method is the investigation of calvic nystagmus. Putting warm water into external acoustic meatus is the same stimulus for the receptor cells as the movement towards the left, to the same side. So there is excitement in the left ampullary crest, and the result of the reflex is to turning the eye turning to the opposite side. When cold water is put into external acoustic meatus, this acts the same way as the movement to the opposite side, so that results in inhibition of the same side. Important to emphasize that for any of these two reflexes, if you want, because these are really reflexes, no cortex of the brain is needed. It means that in comatose patient equally could be evoked, and therefore it's a good sign, a good tool to tell the level of the damage in the brainstem, even in unconscious patients as well. Another example of vestibulo-ocular reflex is tilting the head, and that is the thing what hardly to be investigated in patients, because we've got the round pupil. So tilting the head results in rotation of the eye, and this one is very not obvious in the humans. But looking into details of these happenings, tilting to the left is made by the activity of motor neurons innervating the sternocleidomastoid on tilting the right on the right side. And due to this, at the same time, of course, very good to have inhibition of the contralateral muscle. Good effectivity of the sternocleidomastoid can be reached by this way. So the way how this thing results in the vestibular excitement from the superior and middle vestibular nuclei, second order vestibular neurons through medial longitudinal fascicle go to innervate the eye moving nuclei. So one of these is the nucleus is the oculomotor nucleus. On the same side, the oculomotor gets activated, therefore it results in activation of the fiber innervating the superior rectus of the same side, as well as the superior oblique doing the same, doing the inward rotation, medial rotation of the eye. So the superior oblique is innervated by fibers of the trochlea from the opposite side. This is where you understand why the trochlea is the only cranial nerve coming crossed from the brainstem, so the left one comes from the right nucleus. And that's why simultaneously with the superior rectus it can move, it can be activated, the nerve, and the muscles can move. Opposite side, the antagonistic muscles should receive information, and these antagonistics are the inferior rectus and the inferior oblique muscle, the contraction of which result in outward rotation of the eye of the opposite side. Finally, due to these happenings, the cerebellum informs the lateral vestibular nucleus, and that one sends the informing excitement to the inhibitory neurons innervating muscle of the opposite side. So this one is a picture showing perfect equilibrium in a very young age, and even more perfect you can watch on YouTube. I hope I can project this to you. The problem is that the sound is not too much intensive, so I must be silent. Thank you very much for your attention, and I wish you extreme good luck for this very strange exam period. See you.